All right, so Walker just asked what was allowed on the equation sheet for the next exam. I don't like to call it a cheat sheet. I like to call it an equation sheet because equations are okay, cheating is bad. All right, so it's one page, front and back, handwritten. The reason why it needs to be handwritten is so one very studious student cannot write a really good equation sheet and then distribute it to all of their peers, because I've definitely had that happen before. It needs to be legible without external viewing apparatuses, meaning that if you wear glasses, that's great, but don't show up here with a monocle or a magnifying glass or anything like that, like a jackass, and be like, I'm using this because I wrote really tiny. Off limits. I've also had a student try to write in red ink and also in blue ink, and then wear shitty paper 3D glasses to try to use an equation sheet and put twice as much information on it. Did not go well for him. Don't be a jackass like that. Really, those are the only restrictions. I don't care if you put worked example problems, equations, whatever you want to put on there is fine, but it has to be a handwritten thing. No printouts. Did that satisfy your question? All right. Yes.
So like a plain
Standard 8.5 by 11 sheet of paper. That is correct. Not a legal sheet, not some sort of weird long butcher's paper that extends for 40 yards. Stop being jackasses, just normal paper, for the love of God.
It doesn't have to be like copy paste.
Correct. Yeah, if you want to put it on graph paper, I don't have a beef with that. It doesn't have to be. All right.
I want to see that. I want to see that.
Yeah.
More stupid questions. The bird is back.
All right. So today, let's talk order circuits. Second order filter circuits. Yes, ma'am. Oh, thank you. So much. I'm gonna be so pissed if I have to use it next quarter. All right, so for a second order circuit, we can achieve low pass, high pass, band pass, and band stop filters. So in general, a second order circuit is literally just a series RLC circuit, and we're just choosing which element to take the voltage drop over in order to make a particular type of filter. So let me draw a simple RLC circuit here. So for example, here's my resistor. Here's my inductor. Here's my capacitor. Here's Vn as a function of omega. So I'm just going to do these in different colors, right? So Vr as a function of omega is going to wind in a band stop filter. Nope, band pass. If I take the voltage drop across the inductor, I get a second order high pass filter. If I take the voltage drop across the capacitor, I get a low pass filter. And if I take the voltage drop across both the inductor and the capacitor, I get a band stop filter. So which one do you guys want to look at first? Band stop. Okay. All right, so we'll do the band stop filter first. So in our band stop filter, Just literally redrawing what I just had. Here's my resistor R. Then I have an impedance J omega L, an impedance 1 over J omega C. Here is our input voltage. Here is our output voltage. And our transfer function, H of omega. Just using simple voltage divider relationships here. So in my numerator, I'm going to have J times omega L plus 1 over omega C. Let me make that L more crisp. And then in my denominator, I'm just going to have R plus J times omega L plus 1 over omega C. And once again, because I don't like fractions inside my fractions, I'm going to multiply through. So in this case, I'm going to multiply through by J omega C over J omega C. And that is going to give me 1 minus omega squared LC over 1 minus omega squared LC plus J omega RC. I can then multiply that relationship by the complex conjugate of the denominator over the complex conjugate of the denominator. So just to be clear, 1 minus omega squared LC over 1 minus omega squared LC plus J omega RC times 1 minus omega squared LC minus J omega RC. Same thing up here in the numerator. And this comes out to be 1 minus omega squared LC quantity squared over 1 minus, I don't understand why you're talking while I'm talking. It's pissing me off. Minus J omega RC 1 minus omega squared LC all over the same denominator. So we have it split up into its constituent real and imaginary parts. From here, we can find our magnitude. So our magnitude response, magnitude of H of omega, is going to look like the square root of the real part squared plus the square root of the imaginary part squared. So that's going to look like 1 minus omega squared LC quantity squared 1 minus omega squared LC quantity squared plus omega RC squared, square that whole thing. Over here, I'm going to have negative omega RC 1 minus omega squared LC all over 1 minus omega squared LC squared plus omega RC squared, square this whole thing. And it should be, I hope, fairly obvious that I'm going to have like a 1 minus omega squared LC quantity squared to the fourth power on one side. And then I'm going to have it to the second power on the other side so that I can effectively pull out a common factor of 1 minus omega squared LC. So what this should look like is 1 minus omega squared LC quantity squared times one minus omega squared LC squared plus omega RC squared divided by 1 minus omega squared LC squared plus omega RC squared, square the whole thing. And this guy right here winds up canceling one of those powers, leaving us with 1 minus omega squared LC divided by 1 minus omega squared LC squared plus omega RC squared. When we evaluate this at very low frequencies, we effectively have 1 over 1, right? Because 1 minus 0 over 1 minus 0 plus 0 is going to look like 1. At very high frequencies, we're going to wind up having, so let's look at this really quickly. So in our numerator, it's going to look like negative infinity squared, effectively. In our denominator, we're going to have negative infinity squared squared, so that'll be negative infinity to the fourth power, plus infinity squared, which is just going to be negative infinity to the fourth power. So the negatives cancel each other out, and we're going to have infinity squared over infinity. Oh, sorry, this whole thing down here should be under a square root. My bad. And it's going to look like 1 yet again. So we are passing very low frequencies and we are passing very high frequencies. There's not really a good value of omega to do in the middle to figure out that it dips down there, but we will see very shortly that it'll have a dip in the middle because we're looking at a band stop filter. All right, so if you recall from our lecture on Wednesday, for these second order filters, particularly the band stop filter and the band pass filter, we had a low frequency corner or low frequency cutoff, a high frequency corner or high frequency cutoff, and a resonant frequency in the middle. What do you guys think the resonant frequency of this circuit is going to be? What was the resonant frequency of every RLC circuit we've dealt with in this class? Like when we had a series RLC circuits, when we were doing transient analysis, when we had parallel RLC circuits doing transient analysis, the resonant frequency omega naught was equal to what? 1 over the square root of LC. Exact same thing here because it represents literally the exact same thing, okay? So omega naught is equal to the square root of 1 over LC. This is our resonant frequency. Now, unfortunately for us, or probably actually fortunately for you guys, finding out what frequencies make this equal to 1 over the square root of 2 is not nearly as easy as it was for our first order circuits. So instead of going through a bunch of terrible algebra and all of that kind of stuff, I literally just set this big thing equal to 1 over the square root of 2 in MathCAD and had it symbolically solve things for me so that I would get my different corner frequencies. Now, it turns out that you're going to wind up getting 4 corner frequencies, not just 2. However, 2 of those 4 corner frequencies are actually negative frequencies. So we're going to throw those results away because a negative frequency doesn't really mean anything. How can we have negative cycles per second kind of thing? So using MathCAD, what we'll find is that our low corner cutoff frequency, or sorry, our low cutoff frequency is negative R divided by twice L plus the square root of R over twice L quantity squared plus 1 over LC. And then omega high is positive R over 2L plus the square root of R over 2L squared plus 1 over C. This should look kind of familiar. Okay, I say kind of familiar because this is very, very similar to what we saw for S1 and S2 in a overdamped circuit. However, there is a pretty important distinction here. So when we were dealing with S1 and S2, this first term, alpha effectively, was always negative, and then we changed the sign on the second term. For our cutoff frequencies, it's the same thing, except that we're leaving the sign on the second term to be positive and changing the sign on the first term to go from our low frequency to our high frequency cutoff, right? So these are our -3 dB cutoff frequencies, or -3 dB cutoff frequencies. What would the width of our stop band be? So I'm going to write down here stop band. By definition, that's literally just omega high minus omega low. So somebody do the incredibly easy amount of math here and tell me what the answer should be. What was that? R over L. That's what defines the bandwidth of our filter. So if we were to try to design one of these things, say we wanted a band stop filter with a center frequency or resonant frequency of 1 megahertz, and then we wanted a 200 kilohertz bandwidth, effectively, we could settle on a value for L, just pick a capacitor, or excuse me, an inductor value that's readily available, and then use this equation to figure out what the capacitor would need to be to achieve the center frequency, and then use this equation to figure out what the value of the resistor would need to be to establish our bandwidth. That is as easy as filter design can possibly get, which, by the way, is literally the type of question that I'm going to ask you guys for your filter design homework. So realistically, for the filter design project thing, if it takes you more than 30 minutes, you're doing it wrong. Okay. Our phase response is just going to be the inverse tangent of the imaginary part over the real part. So let's look up here really quickly. Once again, the denominators of each part are the same, so I'm going to throw those away because when we do that fraction, they're just going to cancel out. So we're going to have omega RC times 1 minus omega squared LC over 1 minus omega squared LC quantity squared. And this guy right here gets rid of one of these powers. So we have the inverse tangent of omega RC divided by 1 minus omega squared LC. All right, so let's design something. Let's say that I want I'm trying to remember what the starting frequency of DSL is. Can't remember what it is off the top of my head. Effectively, on so DSL internet, which I'm not even sure if it's really still a thing anymore, was an earlier form of broadband internet, was used over telephone lines, like hardwired telephone lines. So in a telephone line, typically up to about 4 kilohertz was reserved for human voice. And then everything above 4 kilohertz was cut off. Now, some of you might be thinking, but wait a minute, doesn't like the range of frequencies that humans can easily hear and human speaking usually go up to 20 kilohertz? You would be correct. So if you ever listened to, like, let's say some Muzak on a landline telephone back in the day, the reason why it sounded so god awful is because all of the high frequency response of the music was cut off because the telephone company was cheap. Their filters were set to cut things off at, I think it was 4.3 kilohertz. So let's say that we want, just for the sake of argument, omega low to be 2 pi times 4.3 kilohertz. And let's say, just for the sake of argument, that we wanted omega high to be 2 pi times, I don't know, let's say 100 kilohertz. Actually, let's make it ridiculously easy and say that it's 104.3 kilohertz so that I don't have to do remotely difficult math. From this, what should our center or resonant frequency be? $54.3 kilohertz, right? Or times 2 pi. So I want us to design and simulate a system that meets these constraints. We'll test things out, right? So what seems like a reasonable inductor value? 100 millihenry. All right, so 0.1 henries. So we know that omega naught is equal to the square root of 1 over LC. So from this, we should be able to say that omega naught squared is equal to 1 over LC. So C should be equal to, why is my stylus not writing? 1 over L times, sorry, omega naught squared, if I did my math correctly there. Did I do my math correctly there? Okay. So let me grab a calculator and let's see what shakes out here. So 1 over 0.1 times 2 pi times 54.3 times 10 to the 3. Looks to me to be a 29.31 microfarad capacitor. Anybody else get a similar result? Or okay. Our bandwidth, which is just R over L, in this case is 2 pi times omega low, or excuse me, omega high minus omega low, which hopefully is very obviously just 100 kilohertz. And so from here, since we know what L is, R should just be 0.1 Henry times 2 pi times 100 kilohertz. So 0.1 times 2 pi times 100 times 10 to the positive 3. Now I got 62.83 kilo ohms. Now, let's throw this bad boy into LT Spice. Crap, I just closed it. Why won't it let me start? Oh, I just ended the call. Holy shit. Wait, no, I didn't. Oh, I don't even know what's happening then. Whatever. All right, so here's my 62.8K. Let's just call it that. Rounding error is all right. Here is my 0.1 Henry inductance. Here's my 29.3 microfarad capacitance. Input voltage source. Advanced. 1. Throw ground at the bottom. This node right here will be where our output voltage is measured. And we're going to do an AC analysis, decade, number of points per decade, still make it 1,000. Let's see, our start frequency should be pretty low. So let's do 1 millihertz up to 1 megahertz. Throw it up there. Run this bad boy. Look at our output voltage. Make this in blue. So we can see everything that's going on really well. So, effectively what's going on here is we see that all of our signal is getting passed for very, very low frequencies, and then it rolls off, and then all of a sudden here at 100 hertz, did I do some math wrong? 1. Because we should be seeing our center or our resonant frequency of 50 kilohertz, right? So it should be way over. Double check. 62.8, 29.3 micro. Bandwidth is R over L. Just go back here and double check my math really quickly. So omega naught squared is equal to 1 over LC. Multiply both sides through by C, divide both sides through by omega naught squared. I get that thing, 1 over 0.1 times, I have an idea why it might be doing this, but that's fine. 2 pi, just want to double check. Yep, that's checks out. All right. So here's what I think our problem is, and it's coming from our design parameters effectively. Our bandwidth is actually larger than our center frequency. So the only way that's going to possibly work is if it starts rolling off in both directions pretty darn early. So there are other types of filters that we could use for a design like this. What's coming to mind for me would be what's called a Chebyshev filter, because it has a very, very quick roll off. So it has a very quick transition from its pass band into its stop band, like a near vertical transition in a semi-logarithmic plot. So we might have to do something like that for this, which is beyond the scope of this course, right? So realistically, I should have been paying attention earlier when we were setting our design constraints. This is still showing you effectively what a band pass filter, excuse me, a band stop filter is going to do though, right? There's a very distinct notch here in the middle where we stopped passing frequencies. Right here at a little under 100 hertz, we can see that our output signal is 1,000,000 times smaller than our input signal. That's what negative 120 decibels means. Another interesting thing that we see here in this response is looking at the phase diagram, right? So we start at roughly 0 degrees. Actually looks like it might be about negative 20 right here, but over here to the left, if we expanded this thing, it would be at 0 degrees. And then it's transitioning down here to negative 90. And then all of a sudden at the resonant frequency, our phase angle completely switches from negative 90 degrees to positive 90 degrees. So we have phase inversion. It went from 90 degrees positive to 90 degrees, excuse me, 90 degrees negative to 90 degree positive, which means the polarity of our output signal literally switches sign at this specific frequency. And then it winds up settling and then rolling back down to 0 or in phase with our input signal as we get at very, very high frequencies. So that's a pretty interesting thing, because that switch in frequency can be problematic for some applications. So if we used a filter like this in a circuit where we had negative feedback, that phase inversion means that effectively for a certain range of frequencies, we're actually going to have positive feedback, which is probably something that we don't want to have. So that's another consideration that we're going to have to take into account when we're using these things for practical purposes, right? So if we see an abrupt sign change like that in a feedback system, that can literally, what that means is we have a point of instability in our system where negative feedback looks like positive feedback or vice versa. And generally speaking, if we design a system for one type of feedback, we want it to be just that one type of feedback over all frequencies of interest. So anyway, all right. So less informative than I wanted it to be, but the design process here was at least illustrated. And then obviously on the design project assignment, I will give you something that will work out less shittily. Yes, Toby. So the power consumption is going to be based on how much the resistor is absorbing, because we know that the resistor is the only thing that's absorbing average power, right? So the resistor is going to absorb some power, and the capacitor and the inductor. So let me think about how do I put this. The resistor is going to absorb average power regardless of frequency. The amount of power that it absorbs as a function of frequency will probably be different though, but it's the thing that's going to be constantly consuming power. We know that in an AC circuit, so at any given frequency, the average power absorbed by the inductor is 0 and the average power absorbed by the capacitor is 0. So over all frequencies, it should still look like 0 on average. So it's really just going to be a function of what the resistor is doing. So if we wanted to look at that, let me delete this thing right here. So I want to add a trace here. So what I'm going to put in is, actually, let me look at this node. So this is node 001. Okay. So add trace. The voltage at node 001 minus the voltage at node V out. I'm going to put parentheses around both of those things. And then I'm going to multiply this by the current flowing through the resistor, because that's just the voltage drop across the resistor multiplied by the current flowing through the resistor is going to look like the power the resistor is absorbing. What's really interesting to me here, just looking at this guy, is that the response of the power actually looks like how a bandpass filter works. So at very low frequencies, it absorbs practically no power, which should make sense. At very low frequencies, the capacitor is going to look like an open circuit, which means if we don't have a load that we're driving, our output voltage is exactly the same as our input voltage. There's no current flowing through the resistor. At very high frequencies, the inductor looks like an open circuit, and we have the exact same situation. So only in the stop band really is where we should see our resistors actually absorbing any power. So interesting, good question. Okay, so we've talked about a band stop filter. Which one do you guys want to look at next? Band pass. All right, so new. So for a band pass filter, this is the one where we're taking the voltage drop just across the resistor, if my memory serves me correctly. Yep. Yep, absolutely. So here's J omega L. Here's 1 over J omega C. Here's our resistance R. Input voltage as a function of frequency. Output voltage as a function of frequency. Once again, just using simple voltage division, we should see that our transfer function is R over R plus J times omega L minus 1 over omega C. Actually, I did this derivation a little differently, so let me do it how I did it in the notes so I don't struggle through math here. J omega L plus 1 over J omega C, like so. Multiplying through by J omega C over J omega C is going to look like J omega RC in the numerator. Then I'm going to have 1. So when I multiply J omega L times J omega C, I'm going to get negative omega squared LC. And then when I multiply the R by J omega C, I'm going to get plus, go away menu thingy, go away thing, J omega RC, like so. Putting parentheses around that just so that we denote that that's the real part. Thanks. All right, so from here, we can split it up into its real and imaginary parts like we've done previously. So I'm just going to take that ratio and multiply by the conjugate of the denominator. Oops, omega there, or no J there, excuse me. And let's stick it down here. Positive J omega RC times negative J omega RC is going to look like positive omega RC squared. Then I'm going to have a plus J times omega RC times 1 minus omega squared LC. That's my numerator of my imaginary term. My denominator of both terms is going to be 1 minus omega squared LC quantity squared plus omega RC quantity squared. So from here, am I okay to scroll further? Okay. Our magnitude response is just the exact same thing that we've done over and over again. I'm going to square the real part, square the imaginary part, add them together, take the square root of the whole damn thing. And in doing so, it should be obvious that there's going to be a common factor of omega RC squared that we can take out. So we'll have omega RC squared times omega RC times, sorry, 1 minus omega squared LC squared. And then down here in our denominator, we are going to have 1 minus omega squared LC quantity squared plus omega RC quantity squared, this whole thing squared. This guy right here cancels one of those powers in the denominator. And what we're left with is omega RC divided by the square root of 1 minus omega squared LC quantity squared plus omega RC squared. So at very low frequencies, our numerator looks like 0 and our denominator looks like the square root of positive 1. So 0 over 1 looks like 0. At very high frequencies, our numerator looks like infinity, and then our denominator is going to look like the square root of infinity to the 4th power, which is going to look like infinity squared. So infinity over infinity squared looks like 1 over infinity, which once again looks like 0. So we attenuate very low frequencies, we attenuate very high frequencies. We can't really see anything from this relationship, but we'll see when we simulate something here that in the middle, we're going to start passing frequencies because this is a band pass filter. Our resonant frequency, omega naught, is the square root of 1 over LC, just like it was before, because it's just an RLC circuit. Omega low is negative R over 2L plus the square root of R over 2L squared plus 1 over LC. So exact same low frequency corner as our band stop filter. And as it turns out, it will be the exact same high frequency corner as well. Right. So here are our two negative 3 dB cutoff frequencies. Our bandwidth will once again be exactly what Slade figured out, simply R over L. And then lastly, our phase response as a function of omega will be the inverse tangent of omega RC times 1 minus omega squared LC over omega RC quantity squared. So that's going to look like the inverse tangent of 1 minus omega squared LC over omega RC. So let's design something else, but hopefully this time I don't screw it up by giving us unrealistic design parameters. What is Louisiana Tech's radio station? 89.1, KLPI 89.1, okay? So that is going to be our resonant frequency. Omega naught will be 2 pi times 89.1 megahertz. What is the channel separation on an FM radio? 0.2. So you go 89.1, 89.3, etc. So it just the way it was designed. So it's 0.2 megahertz or 200 kilohertz, right? So our bandwidth is 2 pi times 200 kilohertz. Our bandwidth is definitely much smaller than our center frequency this time, so this should work out correctly. All right. All right, so somebody hit me with an inductor value. That's too big. What's something that you could actually purchase? 200, okay, 0.2. Still large, but whatever. You guys are unimaginative. Why not 43.9 microhenries? I don't know. Anyway. So let's say that L is 200 millihenries or 0.2 henries. Okay. So we should be able to use literally the exact same equation that we used before to figure out the necessary capacitor here. So C should just be 1 over L times omega naught squared. So that's going to be 1 over 0.2 henries times 2 pi times 89.1 times 10 to the 6th hertz squared. So let's see what shakes out of this. Holy mother of God. All right. I got 15.953 attofarads, where an attofarad is a 10 to the minus 18 farad. So we're going to be hard pressed to buy a capacitor that small. So maybe we need to revisit that inductor value. Okay. So let's try smaller. Yeah, so let's make this 200 microhenries or 0.2 times 10 to the minus 4 henries. And that should change that by a couple of order of magnitudes. So still pretty gross. 15.953 femtofarads. So still gross, but not horrifyingly gross. Yes. Okay. All right. Femto is 10 to the minus 15. So atto is 10 to the minus 18, femto is 10 to the minus 15, pico is 10 to the minus 12. That's realistically where you can actually start buying capacitors. Nano 10 to the minus 9, micro 10 to the minus 6, milli 10 to the minus 3, et cetera, et cetera, et cetera. You guys should know this. You're engineers, or will be soonish. What?
Where's the range where you stop getting real capacity?
So buying, so like the biggest values of capacitors, like a 1 millifarad capacitor is a big capacitor for like standard electronics. Yeah, so 1 millifarad is not wildly unreasonable, but it's going to be a big chunky guy. For the small values, picofarad is typically where you would see things. So like you will deal with femtofarads of capacitance and even attofarads of capacitance when you're looking at integrated circuits and all of that kind of stuff. Not to get too far off tangent because we only have 15 minutes left of class, but like the capacitance per unit area. Oh, there's a ladybug on my power cord. The capacitance per unit area. There is, it's right here. The capacitance per unit area typically measured in between the metal layers on a MOSFET device and the substrate on a MOSFET device is usually measured in attofarads per square micron. So that is a unit that you'll use if you're doing integrated circuit design type things. That being said, purchasing that size of capacitor is not really a thing here. But we'll stick with this 15.953 femtofarad. It's not wildly unreasonable. We should not be on ladybug watch for the rest of the class, by the way. Ian, what's up? So if we made this a nanohenry capacitor, this would make this, excuse me, a nanohenry inductor would make this a picofarad capacitor, and that would be something that we could actually buy. That's literally just the change that we would make. Yep. So if we go down 1 order of magnitude, or I guess a factor of 1,000 on the inductance, we'll go up, and same thing. So that would be 2 times 10 to the negative 7, and we'll just go from there. All right. Go away. For our resistor, that was 2 pi times our bandwidth, which is 200 kilohertz, times our inductor value, which is now 2 times 10 to the minus 7 henries. And so I'd be willing to bet this is going to be a pretty small resistor, but that's okay. 2 pi times 200 times 10 to the 3 times 2 times 10 to the minus 7. About 1/4 of an ohm, which absolutely purchasable. So let's simulate this guy. And I'm going to simulate it shittily on purpose.
Yeah, but question about the capacitors. They're like different grades you get. 1/3 and the other.
So capacitors are typically organized by voltage ratings. So realistically, the capacitor that you buy is going to be dependent on the voltage that you expect the capacitor to see. One incredibly interesting thing is that if we were to, well, that's a circuit 3 thing. Never mind. We'll talk about accidentally burning out capacitors in circuits 3 quite easily by operating circuits too close to their resonant frequency. But like you might have a system where you're putting like 2 or 3 volts AC in, and the capacitor might see 600 volts because of resonance, which will fry it pretty quick if you're not prepared for it. Anyway. So let me make this circuit look less shitty. So this guy was 200 nano. This guy was 15.9 pico. I believe. And then our resistor was in the ballpark of 1/4 of an ohm. And I'm going to change this just to have a dumb number of points per decade like I've seen students do before. So let's do 50. And because our frequency is at 1 megahertz, our center frequency is at 1 megahertz, let's run this from kilohertz scale to gigahertz scale. The number of points per decade. The number of points every time we increase by a factor of 10. So there's only 10 points from 1 millihertz to 10 megahertz, or excuse me, 1 megahertz to 10 megahertz. There's only 10 points from 10 megahertz to 100 megahertz, et cetera, et cetera, et cetera. So like right here, we can see that our center frequency, let me change the color of this. Is a little bit under 100 megahertz. In fact, it's one tick under 100 megahertz, which would be 90 megahertz. However, it looks like the peak value of our gain is actually at like negative 27 dB, thereabouts. Let's get my cursor. Yep, pretty good eyeball there. Negative 26.395 dB. Does that seem realistic to you? So should our voltage divider, when it's operating at its best possible frequency, make our output signal 13 times smaller than our input signal? No. The reason why we're getting these garbage results is because I didn't put enough points per decade in my simulation. So if I were to zoom in on this thing, so let's look at it from 10 megahertz to 100 megahertz. Notice how it looks kind of janky. It's because it's not smooth, because we don't have as much points or as many points in our simulation as we realistically need, right? So if I were to go back to 1,000 points per decade, rerun this simulation, now it looks like it's actually getting close to the 0 dB that we would expect at the center frequency. It's still not there because I don't actually have enough points even with 1,000. Let's see how janky it looks by kind of zooming in. So looks pretty nice and like a nice stiff peak, so to speak. But if we made it, let's say 10,000 points per decade, so we're increasing the resolution of our simulation, now we can see that it actually hits 0 dB. So that's enough points for our simulation to match what our our expectations are. Sorry. All right, so there's a bandpass filter for us. Practical application: if you wanted to tune a resonant circuit to be able to pick up Louisiana Tech's radio station, this is what you would need. One thing that's kind of interesting about this particular bandpass filter is how stiff that peak is, okay? So this is another topic that we're going to talk about in much more detail in Circuits 3, but there is a parameter effectively for resonant circuits called the quality factor. And quality factor is a ratio of how much energy is lost per cycle, I believe, divided by how much energy is stored per cycle. For a filter like this, where we want high selectivity, meaning we want to pick up our channel of interest, but reject other channels, we want a very, very high quality factor, which means we want a very, very stiff peak. If we didn't have something like this, we would actually hear the other radio stations that are broadcasting at a frequency similar to the station that we're trying to listen to while we're listening to this one. So think about this in the context of cellular, gosh, I can't talk today, cellular telephony, fancy word for cell phone calls and all of that kind of stuff, right? In cell phones, you have hundreds of thousands of users, potentially, all operating on an extremely narrow portion of the electromagnetic spectrum, right? So the filters in our phones have to have incredibly high selectivity so that we get our phone calls and only our phone calls, whereas everybody else's phone calls are almost at the exact same frequency on the network. So the peak for the filter in a cell phone is going to be like crazy pointy because the Q factor is like 200 or more. Anyway, all right, that's enough ranting out of me about electrical engineering related crap for today.